So outline of my presentation is I will give you very brief introduction to nanotechnology, which is actually not necessary, but brief introduction to where I come from and the people who are sort of working with me. And then we use Sri Lankan minerals. So Sri Lankan minerals, and we convert these mundane, cheap, low-cost minerals into highly value-added materials. So we'll discuss about these things, and then using these products, we make solar cells, we generate hydrogen photocatalytically, and also we make fuel cells, and these are in energy applications. In addition to that, we use nanomaterials in health applications, as the way Professor Nalin and Professor Rohini was doing in targeted drug delivery and many other health applications. So, I mean, everyone is biased towards your own place. So, and but we are particularly lucky to have 10th most beautiful university of the world, University of Peradeniya. And as far as beauty is concerned, it's very beautiful, and it's in the middle part of the country. And our world rank is 2,113 Webometric rank, and Sri Lanka rank used to be 2, but now it's 1. So we have beaten Colombo. And please play this video and please turn lights. So enjoy. It's a garden university, as you see. Antana means mountain range we have there. We have 750 hectares for the university. Huge area. Biologists have natural lab. If you are sporty, this is the place. We like this, we like that. This is a legendary Professor Chandra. In his name, he created actually this open air theatre. We have multicultural, multi-ethnic group, so we respect all of them. Buddhist temple, mosque, Hindu kovil, Christian church, and all the religions. Actually, we have 9 faculty. This was done a few years ago. Recently, we established management faculty also. It's a full university. Okay, I hope you enjoyed our beautiful university. So, our research, current research activities, we work on energy conversion and storage, particularly, licensed solar cells were developed long ago, 1991, by Professor Katzel and his team. But still, we use very expensive platinum counter electrode, platinum-based counter electrode. 40% of the cost of the DSC is due to this platinum-based counter electrode. So we try to replace this platinum by very cheap graphite, and we are blessed with very 99 plus pure vein graphite in Sri Lanka. Is one of 5 countries where we have this vein graphite in large quantities. So we can, while we are using them in solar cells, we can add value to this vein graphite in Sri Lanka. And also we have developed an instrument to make transparent licensed solar cells, so that you can print these solar cells on your window, in your house or in your car window. You can print DSC, and that will generate electricity while allowing some visible light to go through, transmit through it. So to do so, we convert local minerals to highly value-added products, like we have impure dolomite. Using that, we have Dr. Sanjeeva here, Dr. Mantilaka here. He converted impure dolomite into various forms of precipitated calcium carbonate and magnesium oxide nanoparticles. I had a big trouble with him because he was writing too many papers in a given month. So he kept me really busy those days. He completed his PhD within 2 years actually, and earning more than 12 index international papers. And then Sanjeev, before that actually Pumnel, there's another girl, did PhD on converting impure apatite. We have impure apatite, which contains fluoro and carbonate groups, to pure hydroxyapatite nanoparticles. And then we use these nanoparticles, which are the materials in your bone, to make custom-made prostheses for orthopedic transplants. And then, as I said, together with one of my students in ITI, we try to make solar-grade silicon from quartz, and he's an excellent engineer actually, although he did chemistry special degree, and he has designed all the instruments and actually fabricated the instruments also to electrolyze at high temperature. And we work on converting graphite to graphene products for application there as well as in many other applications. We make nanotechnological architectures and intelligent and smart textiles, and of course, as I said, custom-made prostheses for orthopedic transplants. We work on targeted drug delivery, and we work on low-cost oxygen reduction catalysts for fuel cells, and also using photon up conversion. We try to harvest more than 55% of IR radiation that is incident on the Earth's surface, which contains IR is more than 50 to 55%, visible is 40 to 45%, and UV is about 5%. So we waste infrared radiation, but if we can harvest infrared radiation for water splitting and for making solar cells, then of course we can have working solar cells in the night also. So my group is huge, and I want to pay tribute to I initiated my research career with my final year BSc research supervisor, Professor Mrs. Kumar, and she was a very kind lady, helped me a lot, and that is how I sort of acquired the taste of research. And then I went to Imperial College to work with very famous Professor John Albury, FRS. And then, of course, I have collaborated with many UK, US, Japan, Germany colleagues, including Professor John Albury, and then several local colleagues as well. And Professor Kumara is a very important person with very good skills in making anything. And of course, some of these students are here, and I have not put everybody there, but pardon me if I miss them, because as of now I have about 18 PhD students working with me. So, of course, I can skip this one. As you know, nanoscale is a size scale between 1 nanometer and 100 nanometer. And nanomaterials are materials with at least one dimension in the nanoscale, which means one scale of 1 nanometer to 100 nanometers. So, nanotechnology is the science, engineering, and technology conducted at this nanoscale. So, Professor Richard Feynman, as you know, is the father of nanotechnology. His famous talk, I'm sure you all know about this. There's plenty of room at the bottom. So we have two approaches to make nanoparticles, top down, because these bulk materials are readily available. Atoms and molecules are readily available. So you can start with big ones and chop them down to nanoscale. And you may have to stabilize them, otherwise they don't like to stay separately. They interact with each other. And atoms, molecules start from the bottom and you go up to make nanomaterials. You cluster them and then make nanomaterials. And nanomaterials are unique because, why nanomaterials? Because they are unique. They have size and shape dependent properties, as you all know. If you take bulk materials, if you cut into two, chop into 4 small pieces, color or thermal properties or mechanical properties hardly change. But in the nanoscale, story is very different. As you see, as you all know, these are all silver nanoparticles. Due to surface plasma resonance effect, they absorb and scatter visible radiation. So therefore they are colored. But depending on size and shape, you can have any color. You can make materials with required color. And also, the advantage is the nanoscale is the surface area, huge surface area, because we keep on breaking big ones into smaller ones. So you take the interior atoms or molecules into the surface. So if you take 1 kilogram of 1 micrometer cube particles, have the same surface area as 1 milligram of 1 nanometer cube particle. So at that extreme end, if you convert 1 micrometer cube particles into 1 nanometer cube particles, you increase the surface area millionfold. So that is the advantage. So in the solid state, interactions are, materials touch with each other through surface, interact through surface. So higher the surface area, the better the material. So in the nanoscale, we have very large surface area. That means that to get the same surface area, we need very small amount of material. So that when you come to nanoscale, you can save material requirement. So they have size and shape dependent properties like chemical properties, reactivity, catalytic activity, stability. All these things depend on size and shape. Physical properties more interesting. Electrical properties, mechanical properties, optical properties, thermal properties. All of them depend on size and shape, particularly when you come to lower end of the nanoscale. For example, melting point of silver is somewhere around 1000 when you take bulk silver. As you come below 10 nanometers, you see that melting point is decreasing drastically. And so if you take about somewhere here, so half that value, 500 centigrade. So that is the advantage of the nanomaterial. So therefore, we can tailor make materials with required properties. So that is the advantage of nanomaterials. And so huge surface area to volume ratio is the importance of these nanomaterials. So most of the constituents are on the surface, so therefore they have very high reactivity, extremely high catalytic activity compared to bulk materials. So actually I work at the University of Peradeniya in Department of Chemistry, and but I collaborate with 3 leading private industries. ATG Institute of Solutions, Lanka Limited, is in Catalytic pre-trade zone. Catalytic is where airport is, and just when you come out of the airport, there is a road in front of that, and that lead into this pre-trade zone. This is interest. Those from abroad, pre-trade zone, as you know, means that you are not taxed here. You can produce materials tax-free, but you can't sell them here. You have to export. You have to export. Textiles Lanka Limited. There's another trade zone in Avisavella. So there also we work with, as Mr. Pratna showed you, there are 5 students, including 2 PhD students of the industry. So they attach to industry, and 3 in my department. They work on various like improved properties for textile materials. And then recently we have started a company industry in Colombo called Hodgkin. Dr. Harshit Upasinghe is the provider, the head of the institute. This private industry where we try to make the latest technology sport cars. Because we know that we can't we can't buy it in Japan or any other countries when it comes to making normal cars. But we have the advantage that, in Sri Lanka, we have this knowledge. Sri Lanka is kind of knowledge hub. We have people with required knowledge and capabilities. So he thought of starting an industry to make electric cars of the latest technology. So he has given me actually the task of making a few things like fast charge station. As you go, you have to charge your battery of your car, electric car, within 5-10 minutes. So that is a big challenge. And also there's another student here. He is working on making flow cell, so that it is an electrical cell, but electrolyte is flowing, so that whatever the reactant is replenished continuously, giving constant voltage. And also recently the Science Corporation showed interest in collaborating with us, and of course I collaborate with the Industrial Technology Institute Colombo also. And when you come to Sri Lankan minerals, as I said, Sri Lanka is gifted with a very high quality natural resources. High quality means some of these are 100% pure. Very high quality natural resources, which include very high quality natural minerals and versatile resources of endemic flora and fauna. So Sri Lankan earth accommodates precious gemstones and pearls, very high quality graphite, 100%. Also, his MSc project in this. So we'll see how we do it. So there's a video here, please play. So this is a simple demonstration where we have niobium 5 dot, silver content dot attached, TiO2. Please play the video. So this is Peradeniya in Kandy has a very mild weather. In the evening at about 5 o'clock, it's fairly very dark in the lab. And now they have a student room, AC room. So we have curtains also. So inside when you turn switches off, all dark. So what you do is you add that catalyst. As you see, it's black in color now. It absorbs in the IR. So he added, what they do is he added very small amount of catalyst. Very small amount. And with water, you put that into the flask. And in that dark, if you look at the bottom here, see you generate gas. Very fast. And we use actually sacrificial some alcohol as whole scavengers, so that we can produce pure hydrogen. But when you produce hydrogen and oxygen, the problem is separation. Then you need gas separation membranes. So oxygen is there in the air. The problem is hydrogen, so we can produce hydrogen. Second one also, please. So Charaka, the last person. This niobium is expensive. So we thought of making it cheaper. So why not copper? Copper is very cheap. This is copper dot Cupric dot TiO2. So, can you play it again, please? See, it's generating hydrogen. So we measured using GC. This is hydrogen at a very high rate. appreciable rate. But there are problems, of course. It doesn't keep on doing that. There are various recombination steps slowing this down. So we are working on tackling these problems now. Okay, thanks. So, as you see now, by using this photon upconversion technology and allowing your catalyst to absorb in the IR radiation, IR range, and converting them into visible or UV for electronic excitations, and using the material that absorb in the visible range and also UV range, you can produce hydrogen from water. So, then of course this is one of my other PhD students who completed years ago. Now he's a senior lecturer in the emerging university, new university, Uvalasa University, Dr. K.G.C. Senaratne, commonly known as Jimmy, and his research was on low-cost catalyst for fuel cells. In fuel cells, as you know, fuel cells, if you talk about the efficiency versus power output, gasoline is there in the lowest range. Steam and gas turbines have high power output but low efficiency. Diesel electric is in between. But fuel cells, in the closer to the theoretical maximum hydrogen fuel cells, when you come to high efficiency range, high output range, at low output range, still it's having high efficiency. So fuel cells are producing, if you use hydrogen as the fuel, you are producing very, very clean energy because hydrogen reacts with oxygen generating water. So your exhaust gives water. So it is not polluting in it is important for the environment. It's blessing for the environment. So the problem in fuel cells is actually there are two reactions. You oxidize hydrogen to H plus and you reduce oxygen to hydroxide. And H plus and OH minus react, giving you water. But the trouble here is that both these reactions are very difficult reactions needing catalysts like platinum. So hydrogen, you see hydrogen is a very small molecule. Hydrogen oxidation is relatively easy, having about 50 millivolt over potential than the usual standard electrode potential. But oxygen reduction is very difficult because it involves is a large molecule breaking double bond and all kinds of difficult things. So it involves about 500 millivolt over potential. So oxygen reduction. So we concentrated on developing new, instead of platinum, low-cost catalyst for fuel cell applications. So our aim is to use a non-platinum group catalyst. Actually, this is Professor Bandar and myself were the supervisors. But before even Dr. Chaturanga, one student is MPhil degree on this one, Yasas Rajapakse. He did his PhD in Australia. And also, Velaj Murthy helped. He was doing different work, but he is a fantastic researcher in those days. When he was working with me for his PhDs from Jaffna University, and he worked in the night also, whole night. So he helped him to do a lot of work. And so in our university, we were the first to use very cheap and mundane materials like polypyrrole electronically conducting polymer, and clay, monoclonal clay nanocomposite. So we found, we found that this nanocomposite is a very good oxygen reduction catalyst. So you can use cathode material in fuel cells. So actually after that we collaborated with Shizuoka University in Japan after this discovery, and we jointly published that in Electrochemical Acta in 2010. And immediately after that, I was contacted by Professor Ashton Acton of Oxford University to get permission to sort of review this work in his famous book. So this Chalcogenides, Advances in Research and Application. So there, this book is available in the Google. You can access it, and there's one page on reviewing our sort of earliest work on this, developing this polypyrrole monomer nanocomposite for oxygen reduction. The others are from Maryland, Oxford, Cambridge, like that. So we are so glad that in between pages of Maryland, Oxford, Cambridge, in some universities in France and Germany, Peradeniya is also there in Sri Lanka. That is, in fact, in the Asian country, that was the only one. The others are American, Harvard, Cornell, like those things. So this is what we did was actually we simply polymerize these materials like monomers, aniline, pyrrole. You know that when you polymerize them, you can convert them to electronic conducting form of polymer in the presence of monomer light. As you know, clay has a hard pack-like structure, layered structure. So what we did was very simple. These cards or these layers in the monomerized structure, they are negatively charged due to osmotic substitution. That higher valent cations are substituted by low valent ones, so that overall you have more negative charge. So to counterbalance this negative charge, you have simple lines like hydrated sodium ions, calcium ions in between these layers, in the interlayer spaces. So these are exchangeable. And you can sell these clays because these interlayer spaces you can expand. So you can exchange these normal cations like sodium ions in sodium monomer to oxidizable cations like iron 2, cerium 4, even silver plus, and all these things, different ions. And then this is in a suspension, water aqueous suspension. You can simply add your monomer, then monomolecules go in there, and in the confined environment, electrode potentials are different. Even silver plus can oxidize aniline pyrrole, you will see. Chromium 6 you can use cobalt 3, nickel 3, etc. Iron 3, they can all oxidize these monomers into their respective polymers which are electronically conducting. So whole material becomes electronically conducting. And they have very high thermal stability, high mechanical stability, and they have many applications. Oxygen reduction catalyst, platinum-free material in fuel cells, and we developed some of these catalysts as anti-corrosive paints and hard electrically conductive material. Their usual polymers are soft. Now when you introduce these layers of monomer like clay, they become hard. And we can make conducting paints, electrochromic devices, because these conductive polymers, when you change the potential, applied potential, the voltage, their color changes. So we publish, there are few of those, but several other publications on these aspects. And of course, the idea came to us because this was this kind of clay polymer nanocomposites developed in 1990s by the Toyota Corporation in Japan for their timing belts. So they use nylon modified with clay as a very strong material for time belt. As you know, time belt must be very strong, right, to stand 100,000 miles on kilometers. And also the other importance is that when these polymers usually have pockets and voids where gas molecules can go. Now when you put this clay platelets, they go and fix into these empty places and sealing the material. So that if you have this clay polymer, say bottle to store, say beer, and you can drink that as a beer. But if you just polymer, you don't see, say, beer in, say, polythene container, because there are plenty of pores for oxygen to diffuse through to oxidize this ethanol into acetic acid. So you don't want to drink vinegar. So when you have these clay materials, they can seal these pores so that you can make lightweight, yet strong materials, gas barrier properties, and many other important properties. So, as you know, cyclic voltammetry is the usual method used to find out this oxidation reduction behavior of materials. So, this is an example, cerium dot polypyrrole. So, cerium 4 is reduced to cerium 3, and pyrrole is oxidized to polypyrrole, oxidative polymerization. And clay is montmorillonite clay, cerium 3 polypyrrole electrocatalyst. So when you have completely nitrogen purged atmosphere, when you go in the backwards with respect to saturated calomel electrode, you don't get any reduction. You see nothing there, no current. But when you have oxygen saturated solution, which has about 1 ppm of oxygen concentration, oxygen reduces. There, of course, you have the two reduction. This is oxygen to hydrogen peroxide and then to hydroxyl lines. So what we need is not the hydrogen peroxide. Hydrogen peroxide in turn can be reduced to hydroxyl lines further. And we need oxygen to be reduced to hydroxyl lines. They have that potential. So we did, there's a scan rate dependence. You can see that is a diffusion control process because peak current is proportional to scan rate per half as in the normal diffusion control process. So you see this peak current increases with the scan rate. When you increase the scan rate from 0, 400 RPM, 900, 1600. So we have chosen these cells because you can easily get a square root. So that is our initial work done by, actually it's also Rajapakse, yes, Rajapakse, one of the students, early students. And then there's Chaturanga. He developed 19 such catalysts. He used different cations to oxidize and different monomers like aniline, pyrrole, 3,4-ethylene diacetylthiophene, we call E dot. When you polymerize aniline, you get polyaniline, pyrrole, polymerize to get polypyrrole, and A dot to P dot. So, most of them are, yes, silver ions, even silver ions can do the job. So, you see that this is a rotating disc voltammetry. You can reduce oxygen to hydroxyl ions. So, this is with different materials. A silver MMG P dot is there. This is a platinum carbon. Platinum carbon is also like that, usual, with the same mass loading. Silver carbon. And just gas carbon electrode, you hardly have anything. Nothing. So this is, as you see, in basic medium, for alkaline forces, this is very useful. You see, there's nothing there, no current in nitrogen saturated atmosphere. But when you oxygen saturated atmosphere, you get huge peaks for oxygen, bands for oxygen reduction. See, silver montmorillonite polyaniline, silver montmorillonite polypyrrole, silver montmorillonite P dot, and silver carbon, red one, and platinum carbon, that one. So they are closer to platinum carbon. Some are better actually, I'll show you. Say iron 2. We use iron 3 as the oxidizing iron. So we get iron 2, polypyrrole MMG. Again, it works. Cobalt 3, when you use cobalt 3, an aniline couple, so cobalt 3 is oxidized to cobalt, reduced to cobalt 2, and aniline is oxidatively polymerized to polyaniline inside monomorillonite. You get nice oxygen reduction. And of course, we worked on most of these catalysts, 19 such different combinations, and also we compared that a palladium carbon nanotube P dot system, platinum carbon system, and palladium carbon system. And you see this palladium carbon nanotube P dot is much better than platinum carbon and palladium carbon both. And you see the first cycle and then 1000 cycle. First cycle is this red one, 1000 cycle is black one. Sorry about that. First cycle is there, 1000 cycle is there. So there's a very small change in its activity, you see, after 1000 cycles. See, platinum carbon is the black one, palladium carbon is the red one, palladium carbon nanotube fed up is the blue one. That is the best one. You get the highest current. So this is a very useful. So far, of course, palladium used to be much cheaper than platinum. From this year onwards, of course, palladium became more expensive due to its heavy usage in fuel cells and other power generation technologies. But if you use this clay electronically conducting polymer systems, their efficiency is close, less than same mass loading of platinum carbon, but they are much cheaper. So that the cost of fuel cell is basically the cost of platinum. So what we did was we wanted to deposit hydroxyapatite nanoparticles on them. But just on the stainless steel, very difficult. Stainless steel is very inert, very difficult to attach anything chemically. So we did a trick. But this titanium dioxide is an amazing material. It sticks on many surfaces, including stainless steel. Using our instrument, we use a very thin layer of titanium dioxide on stainless steel, on which we developed hydroxyapatite coating. And collagen is the biopolymer you have. Instead of collagen, doctors use bone cement, that is polymethyl methacrylate, as we all know, PMMA. So, and then biologists took it and they studied. We did corrosion study. They in the simulated body fluid endowment, and they did other biological cell adhesion, toxicity, and all kind of studies. And then it took several months to get ethical clearance. And we had to show that it's non-toxic at all. And this girl was 11 years old. She could not go to school those days. And then after that, and she was lucky, we made this prosthesis and doctor's transplant. The first custom-made prosthesis in Sri Lanka. And after a couple of weeks, she was fine like that. And then she did O-levels, O-levels also. That's the first national examination. And I'm so happy to tell you that she got 9 A's. There are 9 subjects, and she scored A's for all these things. If she didn't do that, and unfortunately she is her right hand, and doctors tried to train her to right and left hand. I'm a left-hander, but unfortunately this girl couldn't do it. But she lost only 1 year of school, but then she recovered marvelously and scored. And then I think she has done A-level also. Now this is about 7-8 years ago. And doctors, we met at his retirement party day before yesterday. And I was there till 11:30 in the midnight. So that is why yesterday also I had some function. So many students. So these are matured students now. They are weddings. So yesterday I had to sign his registration. So to put in trouble. So anyhow, so after surgery she recovered very well. She is now doing very well. And a few months after, doctor called us in the night. He said, I have a patient from a very rural area called Siambalandua who is having a massive cancer. Right? Only solution is amputation. When the doctor said amputation, the patient in Sinhala, he said, I would rather die cancer rather than getting my leg chopped off. That is what he said. So doctor told us, he's a very kind doctor, actually, very busy person. But he said, there's not any time to do custom made things, but he's 55-year-old person. He said, just a matter of saving his life and limb. So can you make a very quick one? Now this operation takes long time, like say 7 hours they took. You have 11 hours. You can make a prosthesis of 15 to this, approximately this size, give us size. Then of course, he knew the sizes because he is so experienced. Without opening, he can he can estimate size. But because bones and polymethyl methacrylate is there to fix it. So then we said, okay, we will try. We went to the engineering faculty, and then we made one. And then it took about 7.5 hours. By the time doctors have almost you see that they are taking this cans out. The cancer part is that big. I have so many photographs. I didn't have time to put all these things, but huge cancer in there. So they've taken everything out from this knee joint, and then fixed with our prosthesis after doing necessary sort of precautions. And this is about now it's 5 years ago. The man has the patient has his limb saved, we saved his limb, and doctor saved his life and limb both. So this is the second one, third one also we made. But this doctor, this we have dearth of medical doctors, so he's very busy. Despite that, he's attending to all these meetings and everything, giving us advices on what's to be done and everything in his discipline. So now that he got retired, so in the retired party, he promised to spend more time now on this project. So actually now there's India. We went to India, Coimbatore Institute. Now that we have 3D printers, so we can print these materials. In India, of course, they print this prosthesis. Yeah, they showed me hip prosthesis. They have printed using 3D printer. Now you can print thousands using. And our bodies, as you go and you will decide, you can print using 3D printers. So they have a mechanical engineering group. They have a strong group on this prosthesis. They use fish bones. So fish bones are bone materials. So they are using powdered fish bones. They can print prosthesis. So one of the professors showed me the hip joint that he sort of printed using 3D printers. It's a marvelous thing. So this Dr. Mantilaka is making various kinds of there's precipitated calcium carbonate, polymer, nano composites for many applications in paint, rubber, paper. That told me pharmaceutical, toothpaste, textile, and many other applications. And also actually there's Shashi will discuss this one, so I don't have to go through this one. So cisplatin is one of those more toxic drugs that you use for cancer treatment. So this is very effective one, but it reacts with many oil-containing proteins in your blood, and it reacts with our normal cells, so its side toxicity is very high. So therefore, bioavailability is less. You need high dose. So what you do is we make these calcium carbonate nanoparticles, and encapsulate this drug in there for targeted delivery and slow release, as the way this Rohini and Nali they are doing. And we started with this Bulatke, and then run there and continuing finally undergraduate projects, but they are doing marvelous work. And Sashi is no second to Mantilaka now. Within 1 year after last year he graduated, now he has 3 papers, 2 reviews, and presented in 12 international conferences also. So I'll skip that one. So this is now his work is now continued by this boy Gayan Shankar. And I just show this one and finish. This is a super hydrophobic antimicrobial cloth that we made. Can you play this one, please? Normal cloth, you put mud, it sticks. This is the same cloth after modification. You put mud is repelled. So wonderful for school uniforms. Children's play and so PRL is a physical research lab, and they put dye onto that. PRL is the modified cloth, the normal cloth. Dye goes to normal, never goes to this modified cloth. And these are chemicals. Large one, sweater, lot of holes in there, but still, when you put it out, that one, this normal clothes attracts those things, but doesn't stick on the. Even if it sticks, you can easily roll off. To unmodified cloth. See, we try to push it to the normal one, doesn't like modified one. This is nickel chloride. Chemicals, they don't like aqueous solution at all. PRL is modified. Okay, thank you. And as conclusions, I would say that we have developed low-cost solar cells based on materials derived from local minerals. I have derived and developed, we have actually highly efficient water spreading catalyst for hydrogen generation. We are developing low-cost but more efficient electrolytes for use in fuel cells to aid oxygen reduction half reaction. That's a difficult one. And we developed nanomaterials from Sri Lankan minerals for health applications, I showed you. And nanomaterials derived from local minerals were used to make custom-made prostheses, biocompatible, osteointegrating, non-corroding and non-toxic. Nanomaterials were used as carriers in targeted drug delivery. Nanomaterials in health and safety, we use antimicrobials, hydrophobic, anti-pilling and stain resistant, and also this is Amit Paratna showed you anti-static garments and textiles. And let's use nanomaterials for the betterment of the society and better future for our younger generation. Right, thank you very much.